Oh yeah, so it should be a CH3 on there. And then so we talked about how then, since this is composed of only sigma bonds, it can rotate freely. There's free rotation allowed on any sigma bond for the most part. And we can track the energy required to rotate through our eclipsing and gauche positions. So if we were to draw our various orientations, so we have our rotation on the x-axis, and we'll go to 180 degrees, negative 180 degrees, and we have energy on the y-axis. Our highest energy position is going to be where our two CH3 groups are overlapping with one another. So if we have a Newman projection that communicates that, so we have a CH3, hydrogen, hydrogen, and then our other CH3, it's a little cramped. That is going to be our highest possible energy. Now, as we rotate out of that eclipsed position, as we move into a gauche position, and this molecule being symmetrical, so it'll have symmetrical energies, whether you're going positive or negative in the rotation. At some minimum, you are going to be fully eclipsed. So your CH3, hydrogen, hydrogen, and then CH3, hydrogen, hydrogen. So we've entered some state where our steric groups, our atoms, our functional groups, whatever they may be, are not overlapping at all. They're essentially as far away from each other as they can be. Now we can take this, and just for the sake of seeing what it looks like, if we rotate simply the other way, if I can get this to paste, there we go. The other group would simply be if we rotated the other direction. Again, it's a symmetrical molecule, so it doesn't necessarily matter which way we're rotating. Now, if we continue to rotate our molecule, continue to rotate about this sigma bond, we're going to reach another maximum in energy. It won't be the absolute maximum, but it will be a local high point. And this local high point is going to be where we're once again fully eclipsing our steric groups. So our CH3 in the front and our hydrogens are now once again eclipsing, just with something else. Instead, now they're eclipsing with, or our CH3s are eclipsing with hydrogens. And then again, if I just simply rotated that the other direction, then you would get that result. Let me do that. So that would be the CH3 here and the hydrogen there. So again, anytime we're eclipsing, we're at some maximum in energy, but the absolute maximum is where we have the worst groups eclipsing with each other. Now we can continue this to another minimum. And that is where we're going to be once again fully gauche with each other. So at this point, our CH3 groups, our methyl groups, are as far apart from each other as they can be. There are no eclipsing interactions. And our molecule is in this orientation. So that would be our absolute minimum in energy if we're rotating this molecule. Now, if we start to substitute this molecule, if we replace these hydrogens with other groups, like let's say that instead this hydrogen we replaced with an alcohol. So we had instead an OH right here. That would change our energy landscape of what we have, because now this OH is going to start interacting with our groups, and perhaps this OH cares more about being far away from a methyl group than the other methyl group. And so we'll talk a little bit later in lecture how to quantify how much groups want to avoid each other. But keep that in mind, that that is something that we may need to look for in the future. We won't always just be looking at these simple carbon chains. So up to that point, have I lost anybody? Just with that review, kind of review of what we finished with on Wednesday. Okay. So for the most part, again, we want to maximize how far away our groups are from each other, but sometimes that is not possible. There are situations where we can run into a molecule where we cannot rotate things to be, this kind of minimum in energy that we sought, where our groups are as far away from each other as possible. The most notable example where this can occur is if we are in a ring. So if we are looking at something like cyclobutane. So let's look at cyclobutane. So that's just a square. By the way, this molecule does exist, even though it has 90-degree angles. Kind of funky, really explosive because of that, but not important. So let me draw on these hydrogens. So again, cyclobutane, it's a 4-membered ring, pretty simple molecule. But if we look down this molecule, so let's put our eye right here, and we're just going to look down the side of the molecule. What we'll see is, quite a bit of eclipsing interaction. So this molecule, let's draw 2 Newman projections so that we can see both of our bonds. So our Newman projection will look as follows. So we've got a hydrogen coming out here. We've got a hydrogen going up that way. And then we've got our bond going to our other carbon. And so this is looking at the front. So this is where our eye is looking at. And so then our other hydrogens are going to be very significantly eclipsing. And because this is a ring, we simply can't rotate ourselves. If we tried to rotate too far in any direction, we would break the molecule. And that's one of the big reasons why something like cyclobutane is so incredibly unstable, and even to the point of being incredibly explosive. I believe this is actually a controlled substance that you cannot obtain easily. And so that brings in a very large challenge in organic chemistry. If you do ever need a molecule like this, they're incredibly difficult to synthesize and incredibly difficult to hold stable. That being said, the molecule can do some things to try to relax its energy. What it can do is it can do what we call a pucker. It can pucker itself. And that is essentially what we assume it would be, where the molecule can sort of torque itself to where it's doing the best it can to create gauche interactions rather than eclipsing interactions. So instead of being a fully planar molecule, as we might expect here, cyclobutane is going to distort itself to where instead, like I said, it's just going to do the best it can, which is not a great job. So let me draw a different view of that. I'll draw that as a Newman projection. So 1 moment. So what this will end up doing is the backwards groups that are creating the bonds with each other will sort of lift upwards a bit, which will force those hydrogens, like I said, to be as gauche as they can be. Now again, the molecule's not going to do an amazing job at this. There's not a lot of wiggle room in something like cyclobutane, but again, it's going to do the best that it can to try and relieve some of that tension. Now, what we call this type of tension is torsional strain. So torsional strain. So torsional strain is what we refer to as the inherent strain, the inherent eclipsing interactions of any ringed molecule. And they're, especially in small rings like this, they're impossible to avoid, for better or for worse, of course, depending on what you're wanting to do as a chemist. But we see that all the time when we're making these molecules. So we'll say there's torsional strain. So with that much, how is that feeling? Pretty good? Yeah, hopefully not too challenging quite yet. Yeah?
Can you draw the puckering again? I'm just having a hard time visualizing what this actually is.
Yeah, so let me draw like a skeleton view of this. So what we would expect, again, if we're wanting to adhere as closely as possible to our sp3 geometry as we can, we would predict that this would be essentially a planar molecule. And so just as we have over here on the left, like we would expect that if again, we're just trying to follow hybridization. But what's going to happen is, and so let me, again, draw a skeleton view of this. And then there's our carbons going backwards. So our molecule will look kind of like this, where instead of, again, being planar, like if you just make a square, as best as you can with your fingers, like it's just going to point 2 of the carbons upwards, point 2 of the carbons downwards. And that's the type of shape that it's going to get, just to try and, again, relieve some of that torsional strain. So there's a competition going on where it wants to keep these optimal bond lengths. It wants to keep these optimal hybridization geometries. But there's also the torsional strain that's there trying to prevent all of that from happening. And so for something like this, there's so much torsional strain that we can go against what's normally the default and create that puckering situation. So we're going to just arbitrarily, 2 of the carbons are going to point up, 2 of the carbons are going to point down. Do that with your hand if that's convenient to do it that way. Again, as well as you can, make a square with your fingers. This could also be a good plug right now. If you have not obtained a molecular model kit yet, I very strongly encourage that you get one. You will find that as far as MCAT, DAT, GPA goes, a $20 molecular model kit, or however much it is on Amazon or from the stockroom, it very well will be worth it. I can guarantee you that. So, So that's what we see with cyclobutane, at least. Now, obviously, the smaller a ring, the more torsional strain there's going to be. So something like cyclopropane, a 3-membered ring. So cyclopropane which, by the way, does exist sometimes, compared to cyclobutane, compared to cyclopentane, and so on. So we have more torsional strain as we remove carbons, as we have a smaller ring. Yep. As we add carbons, there's more opportunity for for the carbons to wiggle around and relieve that strain. Yeah?
So with cyclopropane, what orientation would it be in? Like when it extremes torsional strain, does it bend as well, or?
Yeah, so what is cyclopentane going to be doing? I want to say it does something, it's like the envelope structure is what we call it, where it's like you end up with 4 sort of planar carbons and then one of them like points up or something. I would need to look that up.
Sorry, for propane.
Oh, propane, cyclopropane. It just does nothing. Yeah, cyclopropane just explodes. So, yeah. Yeah.
Could you repeat that part about the torsional strain again and how removing rings all that reduces that?
Yeah, so the more atoms that we have in our ring, the larger our ring, the less torsional strain there is. The more stable our ring can be. The less atoms we have in our ring, the more unstable it's going to be. The more torsional strain there will be. And, again, just remember, like, if we have tetrahedral geometry, again, pull out your molecular model kit that you're going to obtain, hopefully. Make a triangle. It's, like I've broken one of these before, making cyclopropane. One of these little bonds. So, but I've never done that with cyclohexane. So, and we actually see quite a bit in nature. You'll see this in biochemistry and so on, that Mother Nature actually takes advantage of torsional strain at times. We'll find throughout organic chemistry that alkanes are extremely stable. So if you want to add something to just a boring carbon chain, that's actually incredibly difficult to do. And so the way that Mother Nature achieves that sometimes is by forcing something into a ring so that it can go on, and downstream reactions can go and make our proteins, biomolecules, and so on. So interestingly enough, we actually see this 3-membered ring an interesting amount in biochemistry. Not a ton, but more than you'd expect. So again, we will see those every now and then. So one such ring that we do want to pay special attention to is cyclohexane. So the reason for this is that cyclohexane shows up an interestingly large amount in organic chemistry. And not just because we're here building a curriculum trying to point out oddities, but there really truly are a very strangely large amount of reactions that result in 6-membered rings. So much so that cyclohexane deserves almost its own entire chapter, with how it behaves, its strains that it can experience, and so on. So if we look at, that got loud, sorry. So if we look at cyclohexane, so cyclohexane, I'll make that plural because we're going to look at plenty of these. So just our hexagon, and I know I've even seen some of you have a hexagonal note paper. I've seen a couple of you with those. Cyclohexane is the reason why that hexagonal graph paper exists with a few of you. You're going to be drawing a lot of hexagons all the rest of this semester and next. So if we draw a rough Newman projection of this molecule, let's look down this bond right here. So our Newman projection would give us 2 hydrogens sticking out, and then roughly, 2, I'll let it be gauche. There's quite a bit of carbons in there. So we know there's going to be a good amount of gauche interactions. And then there's just going to be, the rest of the ring in that Newman projection. Actually, if you drew it like that, we're usually not too picky about you making sure you're, zigzagging correctly, adding the right number of carbons. Oftentimes, we're just good saying like, yeah, it's a ring in our Newman projection. But with this, even though we have 6 carbons here, we're still limited in how much we can rotate ourselves. So there's going to be some challenges here. That being said, cyclohexane reaches a point to where there's actually a way for it to achieve almost 0 eclipsing interactions. So it can orient itself to where it's essentially perfectly gauche, all of its steric groups, which is great for stable molecules and medications and such. So what we'll see is that cyclohexane adopts what we call a chair conformation. And this is a structure that I would practice drawing. Get good at recognizing this, drawing this, and manipulating this structure. So the chair structure, the way that we draw this, so the chair is we'll end up with 3 carbons pointing up and 3 carbons pointing down. In a moment, I'll show this on the camera over there with a model, with my model kit, show you what that looks like. But drawn, at least, so if we have 3 carbons up and 3 carbons down, the way that I like to draw this is I'll draw 2 parallel lines at a diagonal, sort of like if I'm about to draw a parallelogram, and then I'll just draw a zigzag connecting the 2, pointing inwards, with 1 closer to the left, 1 closer to the right. So on the top one, if I make that closer to the left, I'll just do a short zigzag and then a longer one as I'm protruding. And then I'll start on the other side. I'll get close to that carbon and then long, out to the first carbon. So that's how I draw that. Again, practice that as best as you can. You're going to be drawing chair structures a lot. So if I do take this to the visualizer, as it's called apparently, if that shows up, there we go. So here is cyclohexane, all prepped for stuff that I'll show you. So again, so cyclohexane is not going to be, it's not flat. If we were flat, then we would have just perfectly eclipsing interactions, which we do not want. So if we even orient that in such a way, we can see that those bonds would be eclipsing, which we don't want. If we instead adopt a chair conformation, what we would do is we would take 3 of our carbons and point those upwards, and 3 of our carbons and point those downwards, to where now we have almost a perfect, if I can get that right, we get essentially a perfect Newman projection. We get perfect gauche interactions if we create this chair structure. And so again, a plug, get a molecular model kit and practice this. Because I believe you can also bring a kit into the testing center. So it's not just for homework, it is also for the exam, so you don't have to think about this on paper. So cyclohexane will adopt, like I said, that essentially perfect Newman projection. So if we draw that, we would have 3 hydrogens pointing upwards, straight upwards. We have 3 hydrogens pointing straight downwards. Oh, thank you. There we go. So we have 3 hydrogens pointing straight downwards, and I'll show you this on the model kit as well once I'm done drawing this. And then hydrogen right there. And then on every carbon we'll have a hydrogen that's pointing vaguely outwards. if I can draw this without getting too muddled. So that's what cyclohexane would look like with all of its hydrogens put in. Now let me put on the rest of these bonds so that we can see visually as well, not just with my bad drawing. So again, so in this chair conformation, I've got to switch the camera. Go. So again, as best as we can see, this camera's a little washed out, but whatever. So yeah, so in this orientation, let's see if we can see it well there. So yeah, so we have 3 carbons pointing straight up, 3 hydrogens pointing straight up, 3 hydrogens pointing straight down. And then on every carbon, we have 1 hydrogen that is pointing, like I said, sort of vaguely outwards. And again, if we look at any bond straight down, like for example, if we look at the carbon right here, we can see we do get a perfect Newman projection. Again, we can rotate across to view any bond through a Newman projection, and we can see how gauche that is. So cyclohexanes are interesting in that they can also do what's called a chair flip. So let me put a group on here, or a couple groups on here. So let's say that I have, let's say 3 chlorines or whatever on my cyclohexane, and all 3 of my chlorines are separated by 1 carbon, so they're all in these outward-facing positions. There is a mechanism to which cyclohexane can enter first what we call the boat position. So when that happens, we go from our chair to where now we have a left and a right carbon that are pointing down, and then the 4 middle carbons are going to be pointing up. And I'll draw this as well so that we can see it both through a model kit and on the lecture notes. But here we have a boat. Let me take off these groups just so that it's also a little more clear. The second lecture is going to love me since I've practiced all of this. So there's our boat. And then when we're in this boat, this is the transition state as we're moving to the other chair. So let me put these groups on again so that it's more clear what I'm trying to communicate. So there we go. So if I start in my chair, I can enter a boat, and then I can enter the other chair conformation. If I can get that. There we go. For now, my groups that are substituted went from being outwardly facing to upwards facing. So whenever we do that chair flip, when we go through our boat, we chair flip, any groups that were outwards are now upwards, or downwards, I guess, if it's that way. And then we can chair flip again and put all of those groups facing out. There we go. So there's going to be a significant difference in these 2 orientations of molecules, so much so that we do have names for when something is in an outward-facing position or a up-down facing position. So give this a moment. So looking at this molecule that we have here, our hydrogens, or whatever groups that are facing straight up and straight down, we are going to refer to these as axial. So these are going to be axial groups. Let me highlight that. So axial. Where then any of our groups that are facing outwards, and left out one axial group. Ugh. Apologies. So any of these groups that are facing outward, we're going to refer to as equatorial. So an equatorial group. So we have axial groups and equatorial groups. So likewise, just so we can see this boat conformation, I will show you what that looks like drawn out. So our chair is going to convert to where two of our carbons are pointing down. I can draw that better. So two of our carbons are facing down or up, while the other four carbons are in plane with each other. And that's what our boat looks like. And again, our boat is going back and forth between the two different chairs. Yes?
Is it almost kind of like a resonance structure where it's just going to be like going back and forth between the two shapes?
Very good question. Is it like a resonance structure where it's going back and forth between the two shapes? So kind of. So it's different from a resonance structure in that we're not moving electrons around. And that's an important distinction. Resonance always includes the movement or the sharing of electrons. Here, this is actually more akin to an isomer. So you might remember from Chem 105, 106 when we talked about the different types of isomers, that's what we would actually refer to this as. We could refer to it as an axial isomer or an equatorial isomer. And we will find that one of the conformations is much more stable than the other, which great segue into what we're doing next. So let's say then that we are substituting this cyclohexane. So let's look instead at this. So one chlorocyclohexane, or cyclohexane. So one chlorocyclohexane. So we have two ways that we can draw this structure. So two different chairs. We have it where we can have the chlorine axial and we can have the chlorine equatorial. So let me draw both of those as best as I can draw the chair. By the way, to draw like the ring flipped chair, the best way I've found to do that is just reverse the direction of your parallel lines and then just do the same thing. So that's how we often will draw the two different chairs. So we have one, again, where the chlorine is going to be axial, and we have one where the chlorine is going to be equatorial. Now, by the way, as I point this out, there is one thing that I would like you to notice. So let's say that this chlorine is upwards facing. Now, I know this is a symmetrical molecule, so dashes and wedges aren't important if you've read ahead, but humor me for the sake of the example. So if this chlorine is facing upwards, it's going to continue to face upwards relative to its other group. So if we have a dashed hydrogen, then that means no matter whether this chlorine is axial or equatorial, it's going to be upwards facing compared to the hydrogen. So below it, there's going to be an equatorial hydrogen. Again, that's relatively below the way that we're looking at it. And if we have the equatorial chlorine, imagine that we're taking this group and kind of torquing it that direction. So our hydrogen is now going to be still below, but it's going to be equatorial below. So keep that in mind as you're doing your chair flip. The way that Dr. Price wanted me to word it is your ups stay up and your downs stay down. So keep that in mind as we are drawing these structures, yeah?
How do you know which carbon you start at for the groups?
So that is why I encourage you to practice and get a molecular model kit. So the question is, yeah, how do we know which carbon we're starting with? So do your homework, do practice problems. Like you'll want to number your carbons if you're worried. Like we can always number, just say that, you know, this is carbon 1, 2, 3, 4, 5, 6. So if my chlorine is on a carbon, it's here. So 1, 2, 3, 4, 5, 6. But then if I'm confused, if I'm starting with just a blank chair, you know, a blank flipped chair, and I'm trying to remember, okay, which carbon does my chlorine go on? You know, you just want to, like, first of all, just make sure that things are correct relative to each other. Like, however you number this chair-flipped cyclohexane, just keep it consistent. Make sure that all of your groups are on a right numbering that you choose. But also remember, your ups stay up, your downs stay down. Everything that was axial is equatorial. Everything that was equatorial is axial. So that's where then I would know, like, okay, this chlorine, doesn't matter where I put it, I just need to make sure that since it was axial, it's now equatorial somewhere. So I'm just going to choose that carbon because it's easy to draw, but I could choose any carbon as long as I'm making it equatorial. And then, again, my hydrogen would be downwards. Yeah.
Why do you draw the parallel lines in the opposite direction?
That's just the conventional way to draw a chair flip. So the question was, why do we draw our parallel lines in the opposite direction for the chair flip? You will find as you're doing your homework questions that very much is one of the best ways to do it. It's kind of hard to communicate like a big reason other than just like as you're practicing this, it'll become pretty clear why, like that's just the quick, easy way to do it. Just draw your parallel lines the other way. And yeah, just trust me on that one. But no is not a satisfying answer, but yeah, do your homework and you'll see. In the back?
Do we need to be familiar with all the transition states and intermediates in the boat chair flip?
Yeah, so do we need to be aware of the transition states? I would say not super in-depth. Like, be aware of what the boat conformation is, but don't worry about how we get to the boat. Don't worry about how we get out of the boat. Just know somehow Palpatine returned. Somehow we get to the boat, somehow we get out of the boat. That's all we care about. Yeah?
And then what carbon would that chlorine be as an equatorial group? What carbon do you between the two?
So it's still the first carbon. Yeah. So if I numbered that, so still 1, 2, 3, 4, 5, 6. So again, because I'm not changing any bonds. Like for the sake of drawing it, maybe I had to rotate it a little bit, which you can see, like, my position 1, looks like it moved, one position over. And that's, again, just another plug, like do your homework and this will become much more natural. But while we're here seeing this for the first time, it is understandably kind of confusing watching, it's, rotating like 30 degrees and all that. But again, trust me. Do your homework and trust me. So, yeah. So anyways, so this chlorine would now be equatorial. And we'll see that the equatorial chlorine is magnitudes more stable than the axial. So way more stable. So we want our groups to be equatorial. We want our groups to be away from each other. So to see that, let's look at a modification of this. Let's say that we added 3 more chlorines. So if I did that, I would now have another set of axial chlorines, where here I would now have equatorial chlorines. And if I just think about what I know about steric, interactions, like imagine, let's use a easy, actually visible yellow. Our groups don't want to be close to each other. And these chlorines, they have electrons. Electrons want to repel each other. If all of my groups that are equatorial, I'm shoving them really, really close to one another. Now, we're not going to see that necessarily in a Newman projection, but we will see that through physical experiments and observations, that anything that is axial is forced close to everything else that is axial. Whereas at my equatorial groups, these have just room to just move around. They're happy. They're not seeing anybody. They're nice and asocial as atoms like to be. So equatorial is, again, like I said, magnitudes more stable. So we have a way to quantify this. We use something called an A value. Now, one would think that stands for like axial value or something. According to Wikipedia, it is actually just the letter A. It doesn't stand for anything. But whatever. I don't have my PhD yet, so I don't get to make the rules. So what an A value is it communicates to us how upsetting is it to have something axial. So how bad is axial? So it'll give us a measure in kcals per mole. And so really it says if we take a group that is equatorial and cause it to be axial, what is going to be the energy requirement for that? So what we'll see, and I'll just give you a list here. I don't think you really need to have this memorized other than just like vaguely be aware. Notice that this pretty much just trends perfectly with atomic radius or functional group radius. But first we'll see that hydrogen is basically free. So it takes 0 kcals per mole to switch a hydrogen from being equatorial to axial. An alcohol, an OH, is about 1 kilocalorie per mole of molecule. Sorry, I don't know why that just smeared into whatever that is. So 1. Sorry, I don't know why it's doing that. Next, a methyl group. Sorry, might need to clean my tip. So a methyl group is going to require 1.7 kcals per mole. Let's see what else we have. An ethyl group, so a CH2CH3 is going to require about 1.8 kcals per mole. And then an isopropyl group, so something like this. So an isopropyl group is going to be really big. That's going to require 2.6 kcals per mole. Now, if we just want to trend, look at the halogens, a fluorine is going to require 0.15 kcals per mole. A chlorine is going to require 0.43 kcals per mole. A bromine will require, actually I believe that should be 2.3, my bad. 0.23. A bromine is going to be 0.38. Sorry, I have no idea why my pen is smearing so bad right now. And then an iodine is going to be, that's the 0.43. So we see two things. So for individual atoms, it trends, again, just perfectly with radius. When we start having functional groups, we see that even, something that's just an oxygen bonded to a hydrogen, that's going to be way bigger than any of the individual atoms. So more atoms is more worse. But with that, again, it's just a size issue. So the bigger our group, the more of an issue there is. And so when we're trying to decide if we have, let's say, we have to choose one thing to be axial and one thing to be equatorial. So if I have like a chlorine that's axial versus an alcohol that's equatorial versus the other way, where I'd have a chlorine and an alcohol, then we would choose the one that has the smallest A value to be axial. So whichever has the smallest A value is the one that simply cares the least. And so that is the one that's going to dominate by far. So that's time right there. So we'll finish this. We have like one last thing that we'll talk about on Monday. But really, I very strongly emphasize, do your homework and practice problems for this. This is extremely difficult to visualize if you've not practiced it a bit. And really, get a molecular model kit. I don't get commissions, but I would do it if I were you.
So in the book, it calls it torsion.